Good morning. I'm hoping everything is working fine. I am testing here some setups for a lecture I'm going to be giving the next week on Tuesday. And since I can't stream that one, I thought I would stream my practice so that anybody interested in the topic gets to see. Before I start, though, I am going to play a tiny little tutorial on how to use the interaction widget thingy that I've added to the right-hand side of the stream. It's a little thing where you can tell me if you understand everything that's going okay, if there's a technical problem, if you have a question, and so forth. So I can easier notice if somebody needs my attention while I'm talking. So I'm going to play the tiny little tutorial video first. If you didn't have time to scan the little QR code, it's the same one that's on the bottom left corner now. And you can just go to tinyurl.com/telsatuelisa if you want to vote. So anytime you want to let me know anything at all, please switch the colors accordingly. And I am going to check the chat if there are any questions. Okay, so what I'm going to be talking about today is how we could use deep learning in actual theoretical mathematics in the field of discrete math. And we're going to be working with a well-known problem called the traveling salesperson problem. So what's this all about? These are problems that have to do with graphs. A graph is a collection of entities. We call those vertices or nodes, like the little dots there, connected by lines that are these edges. And what we're trying to do in the traveling salesperson problem is we want to find out a way to visit every single one of those vertices exactly once using the cheapest possible edges. And the edge cost here, we're using the distance. So the shorter the line, the cheaper the cost will be. So in this particular graph that's shown in the picture, the edge between the 0 and 2 vertices, it's pretty short. But we can't really use that one because we only want to visit each vertex exactly once, and we have to go to vertex 1 that's really far away. So this is an NP-hard optimization problem, meaning that it's very complicated to solve in the general case. But since it's NP-hard, we have the added benefit that if we can solve this problem, we can actually also solve many other very relevant problems, as all of the NP-hard problems have reductions from one another. So if I solve one, I can use the method for solving one also to solve another one. Okay, so how would we go about solving this problem? The most obvious thing would be check out all the options. So we just pick an arbitrary vertex to start at, like the 0, and then we're going to think about after we go to 0, are we going to go to 1, 2, or 3? Then for every single one of these options, we have to think about what's going to be the second step, what's going to be the third step. And then we can calculate the sum of the edge costs for each one of these possible orders of visitation. And we just look at which one costs the least. So in the little graph shown on the top right, we have an optimal visitation order that would be either going from 0 to 2, from there to 1, and from there to 3, and then returning back to the 0. Or, of course, could do the same exact thing in reverse. That instead of visiting 0, 2, 1, 3, we could go 0, 3, 1, 2, which is the same in reverse, and is going to give you the same cost. So when we have just 4 vertices, this is actually pretty easy because we get this tiny little tree and we can just look at what's the best cost. The bad thing is that when I get a larger graph like this one here that now has 6 vertices, this tree is already horrible. It's not a nice little thing where you get to choose the cheapest branch, but we get what's called the combinatorial explosion. We get an exponential number of options that we need to be choosing from. And this is now just 6. Think about if you'd have to make a little tour to visit every single 7-Eleven in town to deliver fresh donuts. There's not going to be 6 7-Elevens. In a city like Monterey, there's hundreds. So this tree is going to be entirely untractable. You cannot work with this because there's too many options. So the first thing that we could do is that we could try to be clever, and while we're considering the options, we would discard those options that have a partial cost that's already higher than the best we have seen. So when we've already completed a few branches, we keep in mind what's the cheapest option we have seen thus far. And then when we're looking at another option, if we're only halfway there, but the accumulated cost is already larger than the best we have seen, then this cannot be the optimum because it's already more expensive. So we're not even going to explore that branch to the fullest. So this is called pruning, and we can reduce the tree, but by just a little. It's still a pretty bad tree to go through, and the computational effort required to go through all the options is going to be very high. So when I'm looking for this best cost, it's called the global optimum because there's not going to be any other visitation order that's going to be cheaper. I can do the exhaustive, check all the options, or the pruned version. I measured the runtime in milliseconds for a few tiny graphs with 8 vertices. This is really easy. 88 milliseconds for the exhaustive, 30 for the pruned one. We're saving some time. But when I'm already trying with 11 vertices, which is not a lot, I'm impatient. I can't even wait for it to finish on the exhaustive one. With 10 vertices, it was taking over 9 seconds on the exhaustive, and 11, I didn't want to wait anymore. With 11, I could wait the pruned one. That was a little bit over 3 seconds. But with 12 vertices, well, again, I lose patience with the exhaustive, and it's almost 24 seconds with the pruned one. So this is very rapidly growing. And if we need to deal with real world problems with, like, let's say hundreds of vertices, none of this is feasible. We can't really do any of this because it's going to take way too long. So what we could do as an option is just to move at random. We start from our interesting vertex that we pick as a starting point. It could be 0, it could be 5, it could be 15. It doesn't matter because we make the full loop. And we just go randomly to a neighbor, and then randomly to a neighbor of the neighbor, randomly of the neighbor of the neighbor of the neighbor. So we just randomly visit all the vertices. And that way we create a solution. It's probably not going to be a very good one, but at least it's going to visit every single vertex once. So we can do this very quickly, but we get very poor results. We get very expensive tours. So we could think about what other things we can do computationally that are quick to compute, but wouldn't be as bad as the random walk. What we could do is we could calculate what's called a minimum spanning tree, meaning that we connect all of the vertices to all of the other vertices by a path using only the cheapest edges, the shortest edges we can find. The problem is that when we do this, we don't actually create a cycle. We have these branches where we have to go visit the end of a branch. Like, for example, over here, we go all the way to the end of the branch, and then we have to backtrack to be able to continue. So now we have to clean up this thing that's cheap and nice and goes everywhere just to make it a cycle. So how can I clean this to make it into a cycle? So first of all, we now have a bound to how expensive the tour is going to be because our tour that we will use will never be more expensive than going back and forth this minimum spanning tree. So this minimum spanning tree has all the most all the cheapest edges. So if I sum all those cheapest edges, I get the cost of the minimum spanning tree. And the optimum, it cannot be cheaper than the minimum spanning tree because it cannot use edges cheaper than these. Plus, it needs one more edge to close the cycle. So this cost that we have now cannot be more than twice the global optimum. So we can keep this in mind that we actually have a bound, an upper bound to how expensive this is going to be when we start making it into a cycle. To make it into a cycle, what we're going to do is we're going to start taking shortcuts. Whenever we get into a dead end and we need to backtrack, we're actually going to skip ahead to the next still unvisited vertex that we would get to if we were actually backtracking. Why can we do this? Since we're using the Euclidean distances between the vertices as our edge costs, we have a mathematical property called the triangle inequality, meaning that when I go from A to B through C, going from A to B through C has to be at least as expensive as going from A to B straight up. So this means that whenever I take a shortcut, the cost of the shortcut cannot be more than it would have been to backtrack all the way. So now we do have something that's a cycle. Problem is that this is now a sucky cycle because we have these really long edges, like the one that goes from 12 to 19 and the one that goes from 19 to 10. Those are really long. So what we're going to do now is a little move called 2-opt. If you pick two edges that you don't like because they're very expensive, like here the A to B and C to D, we could consider instead connecting A to C, then running the opposite direction all the way to B, skipping from B to D, and then following the original tour back to A, because this allows us to wipe away those two edges, and we have created an alternative tour that could be cheaper than before. So if we use this kind of a movement to try how could we improve the bad shortcuts into better shortcuts, and we keep trying this many times, we can actually make our cycle cheaper. So we start with the shortcut version. We apply something called a local search by repeatedly doing these 2-opt movements, and that's going to allow us to get rid of the bad shortcuts and create better ones instead, arriving at a smaller total cost. And since we only keep in mind what's the best one we've seen thus far, and we're never going to accept anything that's worse than the original, we still have the upper bound. So this is still never going to be worse than twice the global optimum. We can do this with a method, for example, simulated annealing, which is a method that's mimicking the way that metals cool down, where we start at a high temperature, meaning that we're accepting worse solutions from time to time to escape something called a local optimum. And then over time, we get more and more demanding and we only accept improving solutions. So we can reduce the cost by iterating, doing these 2-opt movements, using the simulated annealing as the acceptance rule. So basically, we could just run this for as long as we like to get better and better solutions. The bad thing is that we have all these parameters. We have the temperature. We have to decide for how long we're going to be stuck, if we're going to have a global maximum iteration or something. So it's a little unpleasant to use in practice because you never really know when you're done. Okay, so now let's imagine that we don't actually know what the edges cost. We have thus far been operating under the supposition that we know exactly the cost of every single edge, and we're considering possible orderings to figure out how expensive the tour is going to be. In practice, we don't always know what the edges cost, because we could have like the situation like when you're buying flights to go somewhere. you can see that if you connect in Detroit, it's going to be a certain cost. If you connect in Atlanta, it's going to be a certain cost. But it never shows you the actual cost per segment. It only shows you the total cost of the combination. This unknown cost problem, it happens a lot in bioinformatics, where you have to do like actual chemical, medical experiments to determine what something actually costs edgewise. Uh, Usually the graph problems in bioinformatics have to do with like whether a gene is similar to another one, whether some protein has a similar function as another one. So in those settings, we don't always know the edge costs, but we might be able to observe the routes. We might be able to see that, okay, so this is a good one and this is a bad one, but we don't really know the edge costs. Dijkstra's algorithm is it's actually an efficient algorithm, so you don't need it for an NP complete problem, because finding the shortest distance from one point to another, you can do that in polynomial time. So these problems are much harder than Dijkstra. But the algorithms we were using to get the minimum spanning tree, the Prim algorithm and the Kruskal algorithm, for example, those are similar in the sense that they're also polynomial efficient algorithms. But it's a similar idea. Like we have to consider possible ways in which we proceed to find the cheapest way to get to our destination. Okay, so now returning to what happens if we don't actually know what the edges cost, but we could observe that whether this route costs like say $2,000 to fly this way, 1,500 to fly this way, and we don't actually know what individual edges cost. But we would like to be able to differentiate between new unknown proposals. If somebody tells you, hey, what if I fly this way instead? But you don't actually know what it's going to cost. We could use artificial intelligence to try to teach it what's a good way to travel and what's a bad way to travel, even without telling it what the graph is, even without us knowing what the edges cost. So let's make a little experiment using deep learning with exactly this purpose. How can I use artificial intelligence to deal with the situation where I can only observe good and bad routes, but I don't actually have access to the edge data? So what I need first is I need to get a data set that these are good cycles with cheap costs and these are bad cycles with high costs. Then I need to split my data. I need some training data and then some testing data. It's very important that I separate these because I do not want to build my model with the same information I'm going to use to test it with. I need to hermetically separate this. I use some of the data for training, and then I use totally separate data to check whether the model I have built is actually working well. So for every single one of the routes in our sets, we need to assign a label, like whether it's a good route or whether it's a bad route. And how we're going to do this, we're going to, when we're generating the data set, we're just going to compute for every single route, how much does it cost? And then we're going to set a threshold. Let's say, how much can I afford? And we're going to say that the ones that are lower than the threshold are the good ones. We assign the label true. And the ones that are above the threshold are bad routes. We assign the label false. We're going to create a deep learning model, meaning that we're actually building a neural network by layers. We're first going to add an input layer. Now we're just going to work with the input and the output layer. In a little while, I'm going to show a different model where that's also going to incorporate more hidden layers. Then once we have this layered model, we're going to feed to that layered model the training data to fit the model into the training data. So basically what we're going to do is we're going to start predicting the labels Y for the training set X, iteratively optimizing the fit, meaning that there is very little deviation between the Y we're wanting to see and the Y that our neural network is actually giving to us. When we're done fitting, what we're going to do is we're going to use the test set and the test labels to see how well the model is going to perform with that data. So for each one of the test routes, we just show the route to the model. We don't tell it what label we want it to get. We look at the label the model gives us and we compare it to the label that we were expecting outside of the model to see if we have a match or a mismatch. Okay, so what we have here are the routes we're creating. In what order am I visiting the vertices? What's the cost? And whether or not the cost is lower than the threshold. If we put these as such as inputs, these are going to be bad inputs because this is just an arbitrary visitation order. So if we put to an input node that this one's a 0, this one's a 3, this one's a 13, this one's a 14, and this one's a 0, this one's a 12, this one's a 17, this one's a 15, we're actually not structuring this at all. Like it's pretty much just random noise. If we want the model to be able to work with this, we need to think smart about what's the input going to be for the model to be able to learn what are good ways to traverse through this graph. Because remember, these routes are the only thing we're showing the model about the graph. We're not telling it anything about the edge costs. So we could at least tell it the vertices. So instead of using the route as such as input, we're going to use as inputs a list of vertex 0 in which position it's visited, vertex 1 in which position is it visited. Like for example here, 1 is visited in position 0, 2, 1, 2, 3, 4, 5, 6. Here it's visited in around 9, here around 8, here it's visited toward the end. So we're going to remap these visitation order thingies into lists showing us in which position was each vertex visited. So this way, when I feed it to the input layer of the model, the first node is going to correspond to what was the position of 0. The second one is going to be what's the position of 1. Then what's the position of 2. So they're always going to be mapping to certain vertices of my graph instead of being a random noise. So then we just feed this input to train the model, meaning adjusting the kernel weights so that the model is going to output us the label that we're wanting to see. So what we're going to be doing here is iteratively optimizing this. The iterations in the deep learning model, we call those epochs. So what we're doing is we execute the optimizer. We're processing the data by little batches. We do weight updates after each batch. And while the model is training, we are observing the accuracy, which is shown in blue here. We want the accuracy to be higher. Like here during the training, we reach an accuracy of about 0.8 with this particular run. And then we have a loss. The loss is just an error measure between the predicted and the expected labels. We want the error to be going down. So while we keep fitting the data into the model by epoch, our accuracy is rising and our loss is lowering. Then when we're done, it's very important to not interpret these final values as our performance measures, but instead we need to compute the accuracy for the test set and the loss for the test set to see what level those actually settle on. So with this particular data, even though the training ended up well, I had a relatively poor accuracy in the test set when I made this image. Okay, so how do I predict? I can throw in routes that I know. I can tell it that I wanted a certain label, and I can observe whether I got that label. The model I'm using is actually not giving trues and falses. It's giving decimal numbers between 0 and 1. So then what we're going to do is we're going to round these. If they're lower than 0.5, we're going to take them as false. If they're higher than 0.5, we're going to take them as true. Then we can calculate how many correct ones we got and how many incorrect ones we have got. So when there's a mismatch, it's an incorrect. In this case, we wanted a false and we got a true. So this is called a false positive. We got a positive answer when we were not supposed to. The opposite would be a false negative when we were expecting a true and we actually got a false. So we can calculate the accuracies in terms of these matches and mismatches. So now the interesting thing to do would be to see how has this model learned the graph, because we never gave it the edge weights. So basically, what I could try to see is, are the weights that I have learned into the deep learning model actually the edge weights that were in my graph? It develops a matrix that is somehow slightly related to the distance matrix, but the kernel weights are not representing our distance matrix. So the deep learning model, it somehow knows my graph, but it isn't representing my graph the way that I would be. The information about the edges has to be there because it's capable of saying whether a route's going to be cheap or expensive. So it has to have learned that information. But we don't really know internally how it's representing this information. And this problem here that we don't know how it's representing, it's like a problem of explainability or accountability. We know that the deep learning model is producing as results. We know that those results might be even very good, but we don't know really why it's giving those results. So it's difficult to base our decisions on what the model is telling us because the model's internal function are largely a mystery to what we're doing. So if we wanted to try to get like a better idea of how is it exactly counting the routes, we could try putting the hidden layers. So if I have my 5 vertices for this particular model, I could add 5 internal layers, trying to think that maybe the model is going to learn the order in which I should be visiting the vertices. So that when I train the model, the weights would represent that from 0, I go to 1, and from there I would go to 3, and from there I would go to 2, and from there I would go to 4. So this would be another thing to try to make it more explainable, to try to map the layers to the visits that we're actually making into the vertices. We train again, and while doing this, I can get pretty good accuracies, both in the training and the testing, and a relatively low loss, sorry. But the problem is that I'm not really gaining any accountability, any explainability yet, because if we look at the kernel weights, there's no way to know what these things mean. There's no easy structure to interpret what are we going to explain our calculations in terms of. Like we have a model that knows to tell us what's a good route, but we don't know why it thinks it's a good one. And if it says it's a bad one, we don't know why it thinks it's a bad one. It's obvious that it has somehow inferred the edge costs because we are able to do these calculations, but we have no idea why. So basically, we are now able to use deep learning to solve the troubling salesperson problem using a threshold, even when we don't know the edge costs. But we have no idea why it's solving it or how it's solving it. So convincing theoretical computer scientists and mathematicians to work with these models is difficult because the mathematical insight of why is very important for solving these problems. Whereas solving it without having any idea why, it's kind of like black magic, like something spitting out a result, but we don't really know why. So I would like to think that I might be able to inspire you to play with this, to see how it works. I've put all my code in a GitHub repository. We can actually go there, maybe. Let me try to go there. Just 1 second. I'm making a mess out of my OBS. Sorry. Let's add another source. 1 second. There we go. Okay, so let's go to the repository to look at this. So I made a little README here. I'm going to add the recording of what we're doing now here as well. I have an interactive version of the code. So in this Google Colab here, you could run all of the things that I was doing. We can create tiny little instances. We can calculate the trees. And at the end, we have all the problems of the deep learning model. So you could try to work with, for example, if you are able to find a mapping between the model weights and the edge distances in the simple model where I just had the input and the output layers, or if you're going to be able to find a way to map the vertices into the layers in the final version where I was using multiple layers between the input and the output. So if you have any trouble with any of this or any questions, please let me know. The easiest way to get in touch with me if you're not on my Discord server would be through direct messages on Twitter. And I will be very happy to hear any ideas you have about how to use this. The purpose here is mostly educational, but it would also be kind of cool to see if we could apply this kind of an approach to actual research situations in which the edges are either unknown or their costs are laborious to extract in any way. So thank you a lot for letting me talk this through with you guys, and let me know if you have any ideas. Bye now.